Right now, at this very moment, the space between you and the nearest galaxy is growing. Not because anything is moving, because space itself is stretching. Every second, thousands of cubic miles of new emptiness appear between galaxy clusters. But here's the impossible part. This expansion doesn't need anywhere to expand into. We're going to explore how the universe grows without an outside, why distant galaxies break the speed of light without moving, and what the edge of everything actually means. If you enjoy this journey into the cosmos, hit that like button and subscribe. Prepare yourselves. We begin. In 1929, Edwin Hubble pointed a telescope at distant galaxies and discovered something that should not be possible. Every single galaxy he observed was moving away from Earth. Not just a few, not randomly scattered in different directions. All of them, fleeing in every direction at once, as if our planet sat at the center of a cosmic explosion. But we weren't special. We weren't the center of anything. The observation made no sense until Hubble noticed one more detail that shattered our understanding of space itself. The farther away a galaxy sat, the faster it raced away from us. A galaxy 2 million light-years distant retreated at a certain speed. Double the distance, double the speed. Triple the distance, triple the speed. This wasn't random motion. This was a pattern. A relationship so precise it could only mean one thing: the universe itself was growing. Hubble measured this using redshift. When a light source moves away from you, its waves stretch. Blue light shifts toward red. The faster the source retreats, the more its light stretches. Hubble examined the light signatures from dozens of galaxies and found them all shifted deep into the red spectrum. Some moved away at thousands of miles per second, others at tens of thousands. The most distant ones he could detect flew away at speeds that seemed to mock the laws of physics. But here's what really troubled scientists at the time. If everything was moving away from us, weren't we at the center? Didn't that contradict Copernicus, who proved Earth wasn't special? The answer revealed something far stranger than anyone expected. Imagine dots painted on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. Ask any dot which one is the center, and from its perspective, it is. All other dots flee from it equally in all directions. Space works the same way. Expansion doesn't happen from a central point. It happens everywhere at once. Between every galaxy, between every cluster, new space constantly appears. The fabric of the universe stretches. This means a galaxy 1 million light-years away has 1 million light-years worth of expanding space between us and it. A galaxy 10 million light-years away has 10 times as much expanding space. More space equals more expansion equals faster apparent motion. Hubble's discovery meant the universe had a history. If everything was spreading apart now, then in the past, everything must have been closer together. Run the clock backward far enough, and all matter, all energy, all space itself compressed into a single point. Infinite density, infinite heat, the beginning of everything. Scientists eventually called this moment the Big Bang, though Hubble himself never used that term. What Hubble couldn't answer was what came before, or what the universe was expanding into. Those questions would haunt physics for decades. Because if space itself was growing, what was it growing through? What medium allowed this expansion? The answers waiting ahead are stranger than the mystery Hubble uncovered. Forget everything you think you know about expansion. This isn't about objects flying through space. A galaxy 2 billion light-years away isn't rocketing through the void like a spacecraft. It's sitting relatively still. What's moving is the space between us and that galaxy. Picture a ruler made of rubber. Place 2 ants at opposite ends. Now, stretch the rubber. The ants don't walk anywhere. The distance between them grows because the ruler itself elongates. The ants are passengers on expanding material. Our universe works exactly this way, confirmed by countless measurements since Hubble's original discovery. Space has structure. It has properties. And one of those properties is the ability to stretch. When physicists say space expands, they mean new distance literally comes into existence between objects that gravity doesn't hold together tightly. Your body isn't expanding, Earth isn't growing. Our solar system maintains its size. Even our entire galaxy holds together against expansion. Gravity at these small scales overpowers the stretching effect. But between galaxy clusters, separated by millions of light years, gravity's grip weakens. These vast distances have no force counteracting expansion. Space between them genuinely grows. Every second, the gap widens. Not because the clusters move, but because more space appears in the gap. This distinction matters tremendously. If galaxies were simply flying apart through static space, they would obey Einstein's speed limit. Nothing with mass can exceed the speed of light through space. But expansion allows something far stranger. Space itself has no speed limit. A region of space can expand faster than light. In fact, the most distant observable galaxies currently sit so far away that the space between us and them grows faster than light can cross it. This sounds impossible. It violates relativity, except it doesn't. Einstein's equations specifically allow space to expand at any rate. His speed limit applies to objects moving through space, not to space itself stretching. Think of it like a treadmill. You run forward at 5 miles per hour, but if the treadmill moves backward at 6 miles per hour, you move backward relative to your starting point despite running forward. You're not breaking any speed records. The platform beneath you is simply moving faster than you can run. Distant galaxies experience something similar. Light from them travels toward us at light speed, the cosmic speed limit, but the space between us expands faster than light can cross it. The light makes no progress toward Earth. It runs in place on an expanding treadmill. Scientists confirm this effect through precise measurements of the cosmic microwave background, the afterglow of the Big Bang still detectable today. This ancient light shows us exactly how fast space expands in every direction. The measurements match Einstein's predictions perfectly. General relativity, his theory of gravity and space-time, describes expansion as a natural consequence of how energy and matter curve space-time. When you fill the universe with matter and energy, the equations demand that space itself must either expand or contract. A static universe is mathematically unstable. Einstein actually inserted a fudge factor into his equations to force the universe to stay still because he believed it must be static. He called this the cosmological constant. When Hubble proved the universe expands, Einstein reportedly called the cosmological constant his greatest blunder. Ironically, modern physics has resurrected this constant to explain something even more bizarre. Something is making expansion speed up. Word count. 600 words. Chapter 3. The balloon that has no outside. Picture a balloon. Not a balloon floating in a room. Picture a two-dimensional being living on the balloon's surface. This creature can move forward, backward, left, or right along the rubber surface, but it cannot perceive up or down. To this being, the balloon's curved two-dimensional surface represents the entirety of existence. Now, inflate the balloon. From the creature's perspective, its entire universe expands. Every point on the surface moves away from every other point, yet the being never encounters an edge. It never finds a boundary. It never asks what lies beyond the balloon because beyond doesn't exist in its reality. Our three-dimensional universe works similarly, though the analogy breaks down in important ways. We live in 3 dimensions of space. When space expands, all 3 dimensions stretch simultaneously. We don't expand into a 4th spatial dimension the way the balloon expands into the 3-dimensional room. The mathematics suggests our universe might be the entire manifold, everything that exists, not an object sitting inside something larger. This challenges human intuition deeply. We're built to understand containers. A box sits inside a room sits inside a building sits on a planet orbits within a solar system. Every physical thing we've ever encountered exists within something else, but the universe itself breaks this pattern. It's not inside anything. There's no container holding it. The universe is the set of all physical locations. You cannot step outside it because outside isn't a place. It's not that something prevents you from leaving. It's that leaving the universe is a meaningless phrase, like asking what's north of the North Pole. Still, the question nags at us. If the universe expands, doesn't it need room to expand into? The answer hinges on what we mean by expansion. Imagine an infinite grid of tiles stretching in all directions forever. Now double the distance between each tile. The grid still extends infinitely, but it's also expanded. You haven't added new tiles to the edge, because there is no edge. You've simply increased the spacing everywhere. Infinite before, infinite after, yet genuinely larger in a specific mathematical sense. Our universe could work this way: infinite before expansion, infinite during expansion, infinite forever. The expansion doesn't require adding new universe at some boundary. It requires increasing the distance between all points. Whether the universe is actually infinite remains unknown. We can only observe a finite bubble around us, limited by the speed of light and the age of the universe. Beyond that observable bubble, we have no direct information. But even if the universe is finite, it might have no edge. A sphere's surface is finite in area but has no boundary. Walk in any direction and you eventually return to your starting point. Never hitting a wall, never reaching an end, a three-dimensional space can curve back on itself similarly, creating a finite volume with no boundary. You could travel in a straight line through this universe and eventually return home from the opposite direction, having circumnavigated all of existence. Current measurements suggest our universe is very close to flat rather than curved. But close to flat doesn't mean perfectly flat. A sphere with a radius of 1 trillion light-years would look flat to anyone standing on its surface, measuring small patches. We might live on a gently curved manifold, so vast we cannot detect the curvature. What we do know for certain is this: expansion doesn't require an outside. Word count: 600 words. Chapter 4: What we mean by universe. When scientists talk about the universe, they often mean two completely different things. This confusion trips up even careful listeners. The first definition refers to everything that physically exists. All matter, all energy, all space and time, everything real. This is the philosophical or complete universe. It might be infinite, it might be finite. We don't know. It certainly extends far beyond what we can detect. The second definition refers to the observable universe. This is the bubble of space around Earth from which light has had time to reach us since the Big Bang. Picture yourself standing in a dense fog. You can see clearly for 100 feet. Beyond that, everything disappears into white haze. That visible circle around you represents your observable fog. But the fog itself extends much farther. You just can't see it. The observable universe works identically. Light travels at 186,000 miles per second, fast by human standards. But the universe is staggeringly large. Light from the most distant observable galaxies has traveled for over 13 billion years to reach Earth. That light began its journey when the universe was young. The galaxies that emitted this ancient light have since moved much farther away due to expansion. Today, those same galaxies sit roughly 46 billion light-years from Earth. That distance defines the radius of our observable universe. A sphere 92 billion light-years across, centered on Earth. But here's the critical part. That's just what we can see. The complete universe almost certainly extends beyond, possibly infinitely beyond. We're trapped inside an information horizon. Events happening right now, more than 46 billion light-years away, cannot affect us yet. Their light hasn't reached us. Their gravity hasn't influenced us. For all practical purposes, those regions don't exist in our causal universe, but they exist in the complete universe. This distinction matters when discussing expansion. The observable universe definitely has a boundary. It's the sphere of space from which light has had time to reach us. This boundary is not an edge of the universe itself. It's an edge of our vision. An observer in a distant galaxy would see their own observable universe, a different bubble centered on them. Their bubble would overlap with ours partially, but also extend into regions we cannot see. So when we say the universe is expanding, we mean space itself stretches everywhere, both inside and outside our observable bubble. Galaxies near the edge of our vision race away from us at tremendous speeds due to the expansion of all the space between us. Some already move away faster than light can cross that expanding distance. We see them now because we're looking at ancient light they emitted billions of years ago, when they were much closer. But new light, leaving those galaxies today, will never reach Earth. Expansion carries it away faster than it can travel toward us. This creates a strange situation. Our observable universe is growing. We detect new galaxies every year as their ancient light finally completes the journey to Earth. Yet simultaneously, the number of galaxies we can ever communicate with is shrinking. Expansion pushes distant galaxies beyond a threshold where future contact becomes impossible. They cross out of our causal bubble forever. We live in an expanding sphere of vision, watching the universe simultaneously reveal itself and slip away. What lies beyond our bubble might be stranger than anything we've discovered. Word count, 600 words. Chapter 5. The horizon we can never cross. There's a boundary in space you will never cross, no matter how fast you travel or how long you live. Not because some force prevents you, not because the journey is too expensive or too dangerous, because the destination is receding faster than you can chase it. This boundary is called the cosmic event horizon, and it represents the ultimate limit of where you can ever go in this universe. Picture yourself in a spaceship capable of reaching 99% the speed of light. You point toward a galaxy currently 15 billion light-years away and engage the engines. You accelerate until Earth vanishes behind you as a distant blue dot. Decades pass inside your ship. Centuries. You travel for subjective eons, watching new star systems slide past your windows. But no matter how long you fly, that target galaxy grows no closer. In fact, it retreats from you. The space between you and it expands faster than you can cross it. This isn't science fiction. This is confirmed physics. The cosmic event horizon currently sits approximately 16 billion light-years from Earth. Galaxies beyond this distance are receding faster than light, not because they move through space at light speed, which is impossible for massive objects, but because the space between us and them stretches faster than light can traverse it. Launch a photon toward these galaxies today, and it will never arrive. The photon makes no progress. It's running on an expanding treadmill. For humans, this sets an absolute limit on exploration. We can theoretically visit any galaxy currently closer than 16 billion light-years. Getting there would take extraordinary time due to vast distances, but the journey is physically possible. Beyond that horizon, however, every galaxy is forever unreachable. You could leave Earth today in a perfect spacecraft and travel at light speed itself for trillions of years. You would never reach galaxies beyond the event horizon. They exist. We can see their ancient light, but we are permanently separated from them by expansion. This horizon also moves, not outward, as you might expect, inward. As expansion accelerates, the event horizon shrinks. Galaxies that are reachable today will become unreachable tomorrow. Every year, approximately 20,000 stars slip beyond our cosmic event horizon forever. 20,000 stars per year, roughly 2 every hour, each one crossing into a realm we can observe but never touch. The observable universe is not the same as the reachable universe. We can see light from galaxies 46 billion light-years away because that light was emitted long ago, when those galaxies were much closer and well within our reach. But those same galaxies today sit far beyond our event horizon. We see their past. Their present is hidden from us by expansion. Future civilizations born in our galaxy will look up at a smaller sky, seeing fewer galaxies because more will have crossed the horizon. In a very real sense, the universe is becoming lonelier. The network of galaxies we could theoretically visit shrinks as expansion accelerates. This raises profound questions. Are we trapped? Is our observable bubble all that matters? If we can never interact with regions beyond our event horizon, do they exist in any meaningful way for us? Physics suggests they exist. They follow the same laws. They contain galaxies, stars, possibly life. But they're permanently separated from our causal bubble, and that separation is growing. Word count, 600 words. Chapter 6. Redshift, the cosmic fingerprint. Light is a wave, and waves can stretch. When an ambulance speeds away from you, its siren drops in pitch. The sound waves spread out, each peak arriving slightly later than it would if the ambulance stood still. Physicists call this the Doppler effect. Light experiences the same phenomenon. But when measuring distant galaxies, something far stranger happens. The stretching isn't caused by motion through space. It's caused by space itself stretching while the light travels. A galaxy, 1 billion light-years away, emits light. That light begins its journey toward Earth at specific wavelengths. Blue light waves measure roughly 470 nanometers from peak to peak. Red light waves measure about 700 nanometers. But as the light travels through space, the space itself expands. Every light wave stretches with it. A photon that left its source as blue light arrives at Earth as red light. The wave itself has grown longer during the journey. This is cosmological redshift, distinct from Doppler shift. Doppler shift happens when a source moves through space. Cosmological redshift happens because space expands while light crosses it. The effect is the same. Light shifts toward longer, redder wavelengths, but the cause is profoundly different, and the magnitude of the shift tells us exactly how much space has expanded during the light's journey. Scientists measure redshift using spectral lines. Every element emits light at specific wavelengths. Hydrogen always produces a bright line at 656 nanometers when its electrons drop energy levels. This is as reliable as a fingerprint. When astronomers observe a distant galaxy, they see hydrogen's spectral line shifted toward the red end of the spectrum. Instead of appearing at 656 nanometers, it might appear at 700 nanometers, or 800, or in the most distant galaxies, pushed all the way into the infrared range invisible to human eyes. The amount of shift directly calculates expansion. A redshift that doubles the wavelength means space has doubled in size since the light was emitted. A galaxy showing this level of redshift sent its light when the universe was half its current size. Everything was twice as close together. Temperatures were higher. Galaxies were younger. By measuring redshift, astronomers essentially measure time. They see the universe as it was billions of years ago. The most distant galaxies detected show redshifts above 10. Their light has stretched to more than 10 times its original wavelength. These galaxies appear as they were when the universe was less than 500 million years old, tiny, primitive, blazing with newborn stars. We see them not as they are now, but as they were 13 billion years ago. The light has been traveling through expanding space all that time, stretching continuously. But here's what keeps cosmologists up at night. Redshift also tells us expansion is accelerating. When astronomers compare nearby galaxies to distant ones, they expect a specific pattern. Distant galaxies should show more redshift because their light traveled through more expanding space. The relationship should be proportional. Double the distance, double the redshift. Instead, the most distant galaxies show slightly less redshift than expected. This means space expanded slower in the past. Expansion is speeding up. Something is pushing the universe apart with increasing force. We don't know what it is. We've named it dark energy. But that's just a label for our ignorance. It makes up nearly 70% of everything in the universe, yet we cannot detect it directly. We only see its effect in redshift, and the effect is growing stronger. Word count, 600 words. Chapter 7. Every direction looks the same. Stand anywhere in the universe and look around. You'll see galaxies fleeing in every direction. North, south, east, west, up, down. All directions appear identical. This is called isotropy. The universe looks the same no matter which way you point your telescope. At first, this seems to suggest we occupy a special location. After all, if everything rushes away from us equally in all directions, aren't we at the center of expansion? No, and understanding why reveals something profound about the nature of space. Imagine an infinite grid of dots. Each dot represents a galaxy. Now imagine every distance on this grid doubles simultaneously. A dot originally 10 inches from you is now 20 inches away. A dot originally 20 inches away is now 40 inches away. A dot originally 100 inches away is now 200 inches away. From your perspective, every dot moved away, and the farther dots moved faster. But here's the key. Pick any other dot and repeat the exercise from its perspective. That dot also sees every other dot moving away. It also appears to be at the center. In an infinite, uniformly expanding space, every point is mathematically equivalent to every other point. There is no actual center, or rather, everywhere is the center. This principle is called the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. Both statements are observationally confirmed. When astronomers map the distribution of galaxies across the entire observable universe, they find remarkable uniformity. Yes, galaxies cluster in groups. Yes, clusters form larger superclusters. But average over large enough volumes and the density of matter stays roughly constant. The cosmic microwave background provides the strongest evidence. This is the oldest light we can detect, emitted 380,000 years after the Big Bang. It reaches us from every direction in space. Scientists have mapped its temperature across the entire sky with extraordinary precision. The temperature is nearly identical in all directions, 273 degrees below 0 Celsius, with tiny fluctuations of only a few millionths of a degree. These fluctuations matter enormously. They represent quantum variations in density from the early universe. Slightly denser regions eventually collapsed into galaxies. Slightly less dense regions became cosmic voids. But the overall pattern is astoundingly uniform. The universe, in its early state, was smooth. No preferred direction, no center, just a hot, dense, expanding plasma that looked virtually identical from every vantage point. This uniformity creates a puzzle, though. How did regions separated by billions of light years achieve the same temperature? They had no time to interact. Light from one region couldn't reach the other in the early universe's brief history, yet they matched to 1 part in 100,000. It's like finding 2 people on opposite sides of Earth wearing identical outfits, down to the stitching, despite never communicating. Cosmologists call this the horizon problem. Different regions of the observable universe share properties they shouldn't share if they evolved independently. The leading solution involves cosmic inflation, a theory suggesting the universe expanded faster than light for a brief moment right after the Big Bang. This rapid expansion stretched a tiny, uniform patch of space to enormous size. All the regions we now observe actually came from one connected volume, giving them time to reach equilibrium before inflation separated them. Whether inflation actually occurred remains debated, but something made the universe uniform. And that uniformity continues today, with expansion proceeding equally in every direction we can measure. Word count, 600 words. Chapter 8. The expansion rate. is not uniform. The universe expands at a rate called the Hubble constant. Except it's not actually constant. This misnomer confuses students constantly. The Hubble constant changes over time. It was faster in the past. It's slower now, and measurements of its current value depend on where in the universe you look, creating one of the biggest controversies in modern cosmology. Right now, the Hubble constant sits at approximately 46 miles per second per megaparsec. A megaparsec equals 3.3 million light-years. So for every 3.3 million light-years of distance, space expands by an additional 46 miles per second. A galaxy 10 megaparsecs away recedes at 460 miles per second. A galaxy 100 megaparsecs away recedes at 4,600 miles per second. The relationship is linear. Double the distance, double the recession speed. But scientists measuring this value keep getting different answers depending on their method. Measure the cosmic microwave background, and you calculate a Hubble constant of approximately 46.5 miles per second per megaparsec. Measure nearby supernovae and Cepheid variable stars, and you get approximately 48 miles per second per megaparsec. The difference sounds tiny, less than 5%. But this discrepancy has survived years of scrutiny and increasingly precise measurements. This is called the Hubble tension. Either our measurements contain unknown errors, or physics is stranger than current theories suggest. Maybe dark energy doesn't behave uniformly across space. Maybe expansion genuinely proceeds faster in some regions than others. Maybe the universe isn't as homogeneous as we thought. Or maybe our understanding of dark energy is incomplete. Recent observations hint at structure in expansion. Studies mapping the motions of hundreds of galaxies found a peculiar pattern. Galaxies in certain directions move slightly faster than average. Not enough to violate the cosmological principle, but enough to suggest subtle variations in the local expansion rate. We might live in a region where dark energy is slightly weaker or stronger than average. Think of ocean currents. On global scales, the ocean is uniform, salt water everywhere. But locally, currents flow faster in some regions, slower in others. The Gulf Stream races along at several miles per hour. Other regions barely move. The universe might exhibit similar behavior, overall uniformity on cosmic scales, but local variations in expansion rate due to concentrations of matter and dark energy. Another complication involves gravity. Expansion happens where gravity is weak. Dense regions like galaxies, solar systems, and planets don't expand because gravity holds them together, tighter than space pulls them apart. But the boundary between these regimes isn't sharp. There's a transition zone where gravity and expansion compete. Measurements in these zones might yield different expansion rates than measurements in deep intergalactic voids. Some cosmologists propose even more radical ideas. Maybe the Hubble constant isn't constant in time the way we think. Maybe dark energy is evolving, growing stronger or weaker as the universe ages. Most observations suggest dark energy maintains steady pressure, but we can't rule out slow changes. If dark energy is strengthening, expansion would accelerate faster than current models predict. This matters for the ultimate fate of the universe. A constant dark energy leads to a cold, empty future where expansion continues forever but slows asymptotically. A strengthening dark energy leads to the Big Rip, where expansion accelerates until it tears apart galaxies, stars, planets, eventually atoms themselves. Understanding whether the expansion rate varies across space and time determines which future awaits us. For now, the measurements disagree. The universe keeps its secrets, and the tension grows. Word count: 600 words. Chapter 9: Dark Energy, the Invisible Accelerator. 70% of the universe is made of something we cannot see, cannot touch, cannot directly detect. We call it dark energy, but that name hides our profound ignorance. We don't know what it is. We don't know where it comes from. We only know it exists because the universe is expanding faster than it should. In 1998, two teams of astronomers studied distant supernovae, Type 1, a supernovae, to be specific. These stellar explosions are remarkably consistent. They reach the same peak brightness every time because they're caused by white dwarf stars hitting a specific mass limit. Astronomers use them as standard candles. See Type 1 supernova, measure its brightness, and you know its distance. Simple physics. Both teams measured dozens of these supernovae in distant galaxies, expecting to find that expansion was slowing down. Gravity should pull everything together, decelerating the expansion over time. Like throwing a ball upward, it slows as Earth's gravity pulls it back. The universe should behave similarly. Early, rapid expansion, gradually slowing under the weight of all its matter. Instead, they found the opposite. Distant supernovae appeared dimmer than expected. This meant they were farther away than predicted. Space had expanded more than it should have if expansion were decelerating. The only explanation was that expansion is speeding up. Something was pushing the universe apart, with increasing force, overcoming gravity's pull. This was utterly unexpected. So unexpected that both teams checked and rechecked their data for years before publishing. When they finally went public, the physics community struggled to accept it. Accelerating expansion violated intuition. What force could possibly drive this? The answer involved resurrecting an idea Einstein had discarded decades earlier. Einstein's equations for general relativity include a term called the cosmological constant. It represents the energy density of empty space itself. Einstein added this term to balance gravity and keep the universe static, which he believed it must be. When Hubble proved the universe expands, Einstein removed the cosmological constant, calling it unnecessary. But the 1998 discovery brought it back. Empty space appears to have intrinsic energy that creates a repulsive force. This vacuum energy pushes space apart. Unlike matter, which dilutes as the universe expands, dark energy maintains constant density. Imagine a box containing gas. Double the box's volume and the gas spreads thinner, exerting less pressure. Dark energy doesn't work this way. Double the universe's volume and you double the total amount of dark energy. The energy density stays the same. This means, as the universe expands and matter spreads thinner, dark energy becomes the dominant force. Early in the universe, matter dominated. Gravity from all that concentrated matter nearly halted expansion. But as space grew, matter diluted. Dark energy remained constant. Eventually, around 5 billion years ago, dark energy overtook matter's gravitational pull. Expansion began accelerating. That acceleration continues today, growing stronger as matter spreads thinner. We don't know why empty space has energy. Quantum field theory predicts vacuum energy should exist, but the predicted value exceeds the observed value by a factor of 10 to the power of 120. That's not a small error. That's a catastrophic mismatch between theory and observation. Either quantum field theory is fundamentally wrong about vacuum energy, or some unknown mechanism cancels most of it, leaving just enough to explain dark energy. The mystery deepens every year. New telescopes, new supernovae, new measurements, all confirm the same strange fact. Something invisible fills the universe and pushes it apart. Word count, 600 words. Chapter 10. Nothing isn't really nothing. Empty space is not empty. This sounds like philosophical wordplay, but quantum physics proves it's literally true. Take a volume of space and remove every atom, extract every photon, cool it to absolute zero, remove all fields, all forces, all particles. You're left with perfect vacuum. Except you're not. Something remains. Something seethes. The quantum uncertainty principle prevents space from ever being truly still. This principle states that you cannot simultaneously know a particle's exact position and exact momentum. The more precisely you measure one, the less you know about the other. This isn't a limitation of measurement tools, it's a fundamental property of reality. Particles don't have exact positions and momentums. They exist in a state of quantum fuzziness. Apply this principle to fields pervading empty space. Electromagnetic fields, electron fields, quark fields. All fields fluctuate randomly at tiny scales due to quantum uncertainty. For an infinitesimal moment, energy appears from nowhere in the form of virtual particles. An electron and positron blink into existence, live for a fraction of a second, then annihilate back into pure energy. This happens constantly throughout all space. Billions of trillions of virtual particles appearing and disappearing every second in every cubic inch of vacuum. These aren't theoretical constructs. These fluctuations have measurable effects. Place two metal plates extremely close together in a vacuum. The gap between them restricts which virtual particles can appear there. Longer wavelength particles cannot fit. Outside the plates, all wavelengths fluctuate freely. This creates a pressure difference. The vacuum outside pushes the plates together with more force than the restricted vacuum between them. Scientists call this the Casimir effect, and it has been measured with extraordinary precision. The vacuum also affects atoms. An electron orbiting a hydrogen nucleus should emit light continuously and spiral inward, collapsing the atom. Except atoms are stable. Why? Virtual photons constantly pop in and out of existence around the electron, jostling it in random directions. This random buffeting averages out over time but creates tiny measurable shifts in the electron's energy levels. Physicists call this the Lamb shift, after Willis Lamb, who discovered it in 1947. These experiments prove the vacuum contains real energy. But how much? Calculate all the possible virtual particles that could exist in a cubic centimeter of space, add up their energies, and you get a number so absurdly large it predicts the universe should rip itself apart. Something must be cancelling most of this vacuum energy. We don't know what. This is called the cosmological constant problem, one of the deepest mysteries in physics. What's even stranger is that vacuum energy might be the source of dark energy. If empty space has intrinsic energy, that energy would push space apart exactly as observations show. The problem is magnitude. Theory predicts vacuum energy strong enough to tear atoms apart. Observations show vacuum energy barely noticeable until cosmic scales. The mismatch is 120 orders of magnitude. It's like predicting someone weighs as much as the entire observable universe, but finding they weigh 150 pounds. Physicists have proposed thousands of solutions. Maybe different contributions to vacuum energy cancel out almost perfectly, leaving a tiny remainder. Maybe our universe is just one possibility among countless others, and we exist in the rare one where vacuum energy happens to be small enough for galaxies to form. Maybe vacuum energy changes over time, and we live in an era when it's relatively weak. None of these explanations satisfy everyone. The vacuum remains, buzzing with invisible energy that shouldn't exist. Word count: 600 words. Chapter 11. The vacuum has weight. Energy and mass are the same thing. Einstein proved this with his most famous equation. Energy equals mass times the speed of light squared. This means pure energy has weight. Light has no mass, but it has energy, so it has weight. A beam of light passing near a massive object bends due to gravity. Photons fall. And if light falls, then the energy filling empty space also falls. Vacuum energy has gravitational effects. But here's where things get strange. Positive energy normally creates attractive gravity. Mass pulls on other mass. This is gravity as we experience it. Drop a ball and it falls toward Earth. Earth pulls the ball pulls Earth. Mutual attraction. More mass equals stronger attraction. Fill the universe with matter and you'd expect gravity to eventually pull everything back together, collapsing the expansion. Vacuum energy works differently. According to general relativity, energy density creates attractive gravity, but pressure creates gravity too. Positive pressure generates attractive gravity. Negative pressure generates repulsive gravity. Vacuum energy has negative pressure. It pushes rather than pulls. This sounds backwards, but it emerges directly from Einstein's field equations. Think of a piston in a cylinder. Compress the gas inside and it pushes back, trying to expand. This is positive pressure. Now imagine something that pulls when you try to stretch it. Pull the piston out and the substance inside resists, trying to contract. This is negative pressure. Rubber bands have negative pressure. Stretch one and it pulls back. Vacuum energy behaves similarly. It resists expansion of space, but the resistance manifests as a push rather than a pull due to the peculiar mathematics of general relativity. As space expands, vacuum energy maintains constant density. This means the total amount of vacuum energy increases. More space equals more vacuum energy. Each new cubic mile of space brings with it the same energy density as every existing cubic mile. Where does this energy come from? The expansion itself. Space expanding does negative work against the negative pressure of vacuum energy, creating new energy. This sounds like violating conservation of energy, but it doesn't. The gravitational field stores negative energy that exactly balances the positive energy of vacuum. This creates a feedback loop. Vacuum energy pushes space apart. Expansion creates more space. More space contains more vacuum energy. More vacuum energy pushes harder. The effect accelerates over time. Early in the universe, matter dominated and expansion slowed. As matter diluted, vacuum energy took over. Now vacuum energy dominates and expansion accelerates. Eventually, this acceleration will tear the universe apart in a scenario called the Big Rip. If dark energy continues strengthening, expansion will accelerate until the space between atoms grows faster than atomic forces can hold them together. Molecules rip apart, then atoms, then atomic nuclei. Finally, even fundamental particles shred into pure energy. The universe ends not with a whimper, but with everything literally pulled apart by expansion. However, this assumes dark energy keeps strengthening. Current observations suggest dark energy maintains constant density, which would avoid the Big Rip. Expansion would continue forever, accelerating, but never catastrophically. Galaxies would drift apart. Stars would die. Eventually, the universe would reach maximum entropy, cold and dark and nearly empty except for the endless expansion of space filled with vacuum energy. Either way, vacuum energy determines our fate. This energy that shouldn't exist, this repulsive gravity pushing space apart, this mathematical necessity that makes no physical sense. It's the dominant force in the universe, and we still don't understand it. Word count, 600 words. Chapter 12. Metric expansion versus moving through space. A galaxy 1 billion light-years away recedes from Earth at 15,000 miles per second. A galaxy 2 billion light-years away recedes at 30,000 miles per second. A galaxy 10 billion light-years away recedes at 150,000 miles per second. A galaxy 20 billion light-years away recedes at 300,000 miles per second. That's the speed of light. A galaxy 30 billion light-years away recedes at 450,000 miles per second. Wait, that exceeds the speed of light. How? Einstein's special relativity states nothing can move through space faster than light. This is absolute. No particle, no spacecraft, no information can cross space at light speed or beyond. The laws of physics forbid it. Energy requirements become infinite as you approach light speed. Exceeding it is mathematically impossible for anything traveling through space. Yet distant galaxies clearly recede faster than light. Observations prove it. How do we reconcile this? The answer lies in understanding what's actually moving. The galaxies themselves aren't racing through space at superluminal speeds. They're sitting relatively still in their local patches of space. What's moving is the space between us and them. Space itself expands. This expansion doesn't count as motion through space. It's the growth of space. Imagine ants on a rubber sheet, Draw two ants 1 foot apart. The ants can walk across the rubber at maximum speed of 1 inch per second. This is their local speed limit. They cannot exceed it. Now, grab the edges of the sheet and stretch it. The rubber between the ants grows. In 1 second, you stretch the sheet enough that the two ants are now 2 feet apart. Each ant moved only 1 inch by walking, but the distance between them increased by 12 inches due to the rubber itself stretching. From each ant's perspective, the other ant receded at 11 inches per second. This exceeds their maximum walking speed of 1 inch per second, yet neither ant violated any rules. They obeyed their local speed limit. The extra distance came from the rubber stretching beneath them. The ants didn't travel through the rubber faster than allowed. The rubber expanded, carrying them apart. Galaxies work identically. Each galaxy moves through its local space well below light speed, typically just a few hundred miles per second due to gravitational interactions with nearby galaxies. This is proper motion through space. But the space between galaxies expands. Add up all the expanding space across billions of light years, and the total recession speed exceeds light speed. The galaxy hasn't moved through space faster than light. Space itself has grown. This distinction matters when calculating distances. Ask how far away a galaxy is, and you need to specify which distance you mean. There's the distance light traveled to reach us. There's the distance the galaxy was when it emitted that light. There's the distance the galaxy is right now. All three are different numbers due to expansion during the light's journey. A photon emitted by a galaxy 1 billion light-years away travels toward Earth at light speed. But during its journey, space expands. The galaxy moves farther away. The photon still travels at light speed through its local space, but it's running on an expanding treadmill. By the time the photon reaches Earth, the galaxy might be 2 billion light-years distant. This creates strange situations. Galaxies we see today are farther away now than the distance their light traveled to reach us. Their present lies beyond their past. Word count, 600 words. Chapter 13. The universe has no edge. Travel in any direction as far as you want. You will never encounter a wall. You will never reach a boundary. You will never find a sign saying, "End of universe, turn back." The universe either extends infinitely or it curves back on itself. Both possibilities mean no edge exists, no place where space stops. The idea of an infinite universe troubles people. Infinite means no end. Travel forever, and you're always somewhere in the middle, with infinite space ahead and infinite space behind. Every point is equivalent to every other point. There's no center, because everywhere is equally valid. This seems to violate the Big Bang model, which suggests everything began at a single point. How can a single point expand into something infinite? The resolution requires thinking carefully about what the Big Bang was. It wasn't an explosion of matter into empty space. It was the expansion of space itself. If space is infinite now, it was infinite at the Big Bang too, just infinitely dense. Every point in infinite space contained infinite energy compressed to infinite density. The Big Bang happened everywhere simultaneously. There was no central point where it originated. Picture an infinite grid of dots stretching in all directions. Each dot is 1 inch from its neighbors. This represents the universe 1 second after the Big Bang. Now expand the grid. Each dot is now 2 inches from its neighbors. The grid is still infinite. You haven't added new dots to the edges because there are no edges. You've simply increased spacing everywhere. The grid doubled in size while remaining infinite both before and after. Our universe works this way: infinite before, infinite after, yet genuinely larger in the sense that distances between all points increased. This is metric expansion. The metric, or measurement of distance, changes. The universe grows not by expanding into something, but by increasing the spacing between everything. Alternatively, the universe might be finite but unbounded. Picture the surface of a sphere. It has finite area, but no edge. Walk in any direction and you eventually return to your starting point, having circumnavigated the sphere. You never hit a boundary. The surface curves back on itself. Now imagine a three-dimensional space doing something similar. Instead of curving in 2 dimensions like a sphere's surface, it curves in 3 dimensions. This is hard to visualize because we're embedded in the space. We cannot step outside and see the curvature the way we can look at a sphere, but mathematically, it's perfectly consistent. A 3-dimensional space can close back on itself, creating finite volume with no boundary. Travel far enough in one direction and you'd eventually return from the opposite direction, having gone around the universe. Current measurements suggest our universe is very close to flat. If it curves, the curvature is so gentle we cannot detect it over the observable universe's scale. This means if the universe is finite and curved, it's vastly larger than the observable universe, perhaps trillions of light years across. So large that the curvature is negligible over distances we can measure. Whether the universe is infinite or merely enormous beyond comprehension doesn't change the fundamental point. You cannot reach an edge. There's nowhere that space stops and something else begins. The universe is everything, all places, all distances. There's no outside, because outside would be a place, and all places are already inside the universe. This leads to the question that started everything. If there's no outside, what is the universe expanding into? Word count: 600 words. Chapter 14. Finite but unbounded. Imagine you're a 2-dimensional creature living on the surface of an expanding balloon. Your entire reality is the rubber surface. You can move forward, backward, left, right, but up and down don't exist in your experience. Now someone asks you, what is the balloon's surface expanding into? You'd be confused. From your perspective, there is no into. The surface simply grows. Distance between all points increases. That's expansion. No 3-dimensional room required. We face the same situation, but 1 dimension higher. We live in 3-dimensional space. It expands. Distances between all points increase. When someone asks what space expands into, they're imagining a 4-dimensional container holding our 3-dimensional universe. But general relativity doesn't require this container. Space itself is the fundamental entity. It doesn't expand into anything, it just expands. This is profoundly difficult to accept because every expansion we've ever witnessed involves objects growing into surrounding space. Inflate a balloon, and it expands into the room. Bake bread, and it rises into the oven's space. Explode a bomb, and debris flies into the surrounding air. These are all expansions of objects through space. Universal expansion is expansion of space itself. There's no surrounding medium. Think of it mathematically, rather than physically. Space is described by a metric, a set of numbers telling you the distance between any 2 points. When space expands, the metric changes. Distances increase. You can write down equations describing this change without ever mentioning anything outside the universe. The mathematics is self-contained. The expansion is an intrinsic property of the space, not motion into something external. But doesn't expansion require more room? No. If space is infinite, it remains infinite during expansion. Infinite before, infinite during, infinite after. The infinity doesn't grow larger in cardinality. It grows in the sense that distances between points increase. An infinite space can expand by increasing its metric without requiring additional infinity. If space is finite but unbounded, the same logic applies. A sphere's surface has finite area but no boundary. Inflate the sphere and the surface area increases. You haven't added new surface beyond the original boundary because there was no boundary. You've simply made the existing surface larger. A 3-dimensional space can do the same. Finite volume increasing without requiring external space to expand into. Some physicists propose higher dimensions might exist. String theory suggests 10 or 11 dimensions, most of them curled up extremely small. Perhaps our 3 spatial dimensions expand through these higher dimensions. This is possible, but it's not required by general relativity. Einstein's equations describe expansion perfectly well in 3 dimensions without invoking extra one. The higher dimensions, if they exist, would add complexity without explaining anything expansion doesn't already explain on its own. The real answer is that expanding into is the wrong framework. It assumes space is an object inside a container. Space isn't an object. It's the stage where objects exist. The stage can grow without needing a larger theater to contain it. This is counterintuitive because our brains evolved to navigate 3-dimensional environments where everything exists in space. We don't have intuition for space itself changing. Language fails us here. We don't have good words for this concept. Expansion suggests growing into something. Universe suggests a container. Every metaphor breaks down because all metaphors reference objects in space. And the universe is not an object in space. It is space. The universe isn't expanding into anything. It's simply becoming more spacious. Word count, 600 words. Chapter 15. The shape question. The universe has a shape, not the distribution of galaxies, not the structure of clusters and voids, the shape of space itself. 3 possibilities exist, each with profound implications. Space could be flat, like an infinite sheet. Space could be positively curved like a sphere. Space could be negatively curved like a saddle. Which shape describes our universe determines its ultimate fate. Flat space means parallel lines remain parallel forever, travel in 2 directions at right angles, and those paths never converge or diverge. Euclid's geometry applies. The angles in a triangle add to exactly 180 degrees. This is the space we intuitively imagine. Infinite extent, no curvature. If the universe is flat, it will expand forever, eventually becoming cold and dark but never ending. Positively curved space means the universe is like the surface of a 4-dimensional sphere. Parallel lines eventually converge. Triangles have angles summing to more than 180 degrees. Travel far enough in one direction, and you return from the opposite direction, having circumnavigated the universe. If space is positively curved, the universe is finite. It contains limited volume, though still enormous beyond human comprehension. The curvature might also affect expansion, potentially allowing gravity to eventually reverse it, causing a big crunch where everything collapses back together. Negatively curved space resembles a saddle extending infinitely. Parallel lines diverge. Triangles have angles summing to less than 180 degrees. This geometry is called hyperbolic. If the universe has negative curvature, it's infinite and will expand forever, accelerating as dark energy dominates. So, which is it? Astronomers measure curvature by examining the cosmic microwave background. This ancient light reveals the size of temperature fluctuations in the early universe. The apparent size of these fluctuations depends on the geometry of space between us and them. In flat space, light travels in straight lines. In curved space, light paths bend. This changes the apparent angular size of distant objects. Measurements from satellites like WMAP and Planck show the universe is extraordinarily close to flat. The curvature, if any, is less than 1%. This means if the universe is curved, it's curved so gently that over billions of light years, the effect is barely detectable. The observable universe represents a tiny patch of something much larger. Like measuring the curvature of Earth by examining 1 square mile, the curvature exists but appears flat at small scales. Why would the universe be so precisely flat? This seems like an unlikely coincidence. Curvature changes over time. A universe starting with even slight curvature should evolve to become more curved as it ages. For us to observe near-perfect flatness billions of years after the Big Bang suggests the initial conditions were extraordinarily fine-tuned. The universe would have needed to start flat to within 1 part in 10 to the 60. Cosmic inflation explains this. If the universe underwent exponential expansion in its first fraction of a second, any initial curvature would have been smoothed out. Imagine a wrinkled balloon. Inflate it to enormous size, and the wrinkles vanish. The surface appears perfectly smooth. Inflation did the same to space, stretching it so large that curvature became negligible. Current evidence favors flatness, but cannot rule out extremely gentle curvature. We may never know for certain whether the universe closes back on itself or extends infinitely. The curvature, if present, might be so slight we'll never measure it. But the question matters, because the shape of space determines the shape of eternity. Word count, 600 words. Chapter 16. What inflation did in the first second. In the first fraction of a second after the Big Bang, the universe did something impossible. It expanded faster than light, much faster. In less time than it takes light to cross an atom, space grew from subatomic size to larger than our observable universe today. This period is called cosmic inflation. It lasted perhaps 10 to the negative 32 seconds. During that infinitesimal instant, the universe doubled in size at least 60 times. Each doubling took a fraction of a second. Before inflation, the entire observable universe was smaller than a proton. Everything we see today occupied a space so tiny that quantum effects dominated completely. Then inflation hit. Space stretched exponentially. The tiny patch ballooned to cosmic proportions. When inflation ended, the universe was perhaps a few inches across, still tiny by cosmic standards, but vastly larger than before, and it continued expanding, though now at a more leisurely pace. Why did this happen? The leading theory involves quantum fields similar to the fields that create dark energy today. In the universe's first moments, temperatures were so extreme that particles we consider fundamental hadn't formed yet. Only quantum fields existed, fluctuating wildly. One of these fields, called the inflaton field, sat in a high-energy state. This state created negative pressure, just like dark energy does now. Negative pressure drives exponential expansion. The inflaton field was unstable. It wanted to roll down to a lower energy state, like a ball sitting on a hilltop. But quantum effects kept it balanced for a brief moment. During that moment, its negative pressure drove space to expand exponentially. Eventually, the field rolled down the hill, releasing its energy. This energy converted into ordinary matter and radiation. The temperature spiked. The universe filled with a hot plasma of particles. Inflation ended. Normal expansion began. This explains several mysteries. First, the uniformity problem. The cosmic microwave background has the same temperature everywhere. How did regions separated by billions of light years reach thermal equilibrium? They never had time to interact unless they came from the same tiny region. Inflation solves this by stretching one small, uniform patch to enormous size. All the regions we observe today came from a single connected volume before inflation. Second, the flatness problem. Why is the universe so close to geometrically flat? Inflation stretched space to such enormous size that any curvature became negligible, like inflating a balloon to planet size. The surface appears flat to anyone standing on it. Third, the horizon problem. Why don't we see certain exotic relics predicted by particle physics? Things like magnetic monopoles, which should have formed in the early universe but have never been detected. Inflation diluted these relics to near zero density by expanding space faster than they could form. Inflation also explains the origin of structure. Quantum fluctuations in the inflaton field created tiny variations in density. Inflation amplified these quantum jitters to cosmic scales. When inflation ended, these density variations seeded the formation of galaxies. The pattern of fluctuations matches observations of the cosmic microwave background precisely. This is inflation's greatest triumph. It predicted the specific pattern of temperature variations we observe in the ancient light. Yet inflation remains controversial. No one has directly detected the inflaton field. We don't know what particle or force causes it. Multiple versions of inflation exist, each making slightly different predictions. Some versions predict infinite eternal inflation, where inflation never completely ends but keeps creating new bubble universes forever. One thing is certain: the universe's first moment was stranger than anything that came after. Word count: 600 words. Chapter 17. Before there was time. Ask what happened before the Big Bang, and you've asked a question that might be meaningless. Time itself began at the Big Bang. General relativity suggests space-time is a unified fabric. Space and time are interwoven. If space emerged at the Big Bang, so did time. There was no before. The word before implies a time prior to another time. But if time didn't exist yet, prior has no meaning. Imagine asking what's north of the North Pole. The question sounds reasonable until you think carefully. North means toward the North Pole. At the North Pole itself, every direction is south. There is no north of north. Similarly, before means earlier in time. At the beginning of time, there is no earlier. Every moment is after. The Big Bang is the temporal equivalent of the North Pole. This frustrates intuition. We want to know what caused the Big Bang, what triggered it, what existed beforehand. Every effect we've ever witnessed had a cause. Chain of causes extends backward indefinitely. Fire comes from fuel and oxygen and heat. Fuel comes from plants or petroleum. Plants come from sunlight and carbon dioxide. The chain continues. But the Big Bang breaks this chain. It represents the beginning of causation itself. Some physicists propose the Big Bang wasn't truly the beginning. Quantum gravity, a theory attempting to unify quantum mechanics and general relativity, might allow time to exist differently at extreme scales. Perhaps the universe bounced from a previous collapsing phase. Perhaps time is cyclical, with endless expansions and contractions. Perhaps our universe budded off from another universe, and time continued across the transition even though space reformed. These ideas remain speculative. We have no evidence for anything before the Big Bang. The cosmic microwave background represents the oldest light we can detect, emitted 380,000 years after the Big Bang. Before that moment, the universe was opaque to light, too hot, too dense. Photons couldn't travel freely. Looking further back requires different methods. Some physicists study quantum fluctuations in the cosmic microwave background, hoping to find signatures of events before inflation. Others examine the distribution of galaxies, looking for patterns that might reveal pre-Big Bang physics. So far, nothing conclusive has emerged. The Big Bang remains an impenetrable barrier to observation. Philosophy intersects physics here. If time began at the Big Bang, did the universe create itself? Can something come from nothing? What does nothing even mean in a quantum context? Quantum mechanics suggests empty space seethes with virtual particles. True nothingness might be unstable, spontaneously spawning universes. If quantum fields are fundamental and don't require space-time to exist, they might fluctuate even when space-time doesn't exist, occasionally producing a universe. This leads to the concept of a universe from nothing. Not nothing in the everyday sense, nothing in the quantum sense. A state with no space, no time, no matter, but still governed by quantum laws. A fluctuation in this quantum void could create space and time together, launching a Big Bang. The universe wouldn't need a prior cause. It would be a spontaneous quantum event, probabilistic rather than deterministic. Yet this pushes the question back one level. Where did quantum laws come from? If they existed before space-time, what substrate do they exist in? The answer might be that physical laws don't exist in anything. They simply are, fundamental and uncaused. Or perhaps they're mathematical necessities, and the universe exists because existing is the only logically consistent option. We don't know. We may never know. Time itself guards the secret. Every year, we see farther into space. Not because our telescopes improve, though they do, because light from more distant galaxies finally completes its journey to Earth. The observable universe expands at the speed of light. Each year, Light travels one more light year toward us from previously invisible regions. This adds a shell of new galaxies to our visible bubble. Picture standing in fog. Your vision extends 100 feet. As the fog slowly thins, your visible radius grows. New trees and buildings emerge from the haze. The observable universe works similarly. The fog is time. Light needs time to cross space. Galaxies far enough away sent their light billions of years ago. That light is still traveling. We cannot see those galaxies yet, but eventually their light will arrive. This means the cosmos is revealing itself gradually. The Big Bang happened 13.8 billion years ago. Light has had 13.8 billion years to travel through space. But space has expanded during that journey. The most distant observable objects currently sit 46 billion light-years away due to the expansion that occurred while their light traveled. This defines our cosmic horizon. Beyond that distance, light hasn't had time to reach us yet. But here's the peculiar part. The observable universe is growing, but the number of galaxies we can ever interact with is shrinking. These seem contradictory. Both are true. We see more galaxies each year as ancient light arrives. Yet more galaxies slip beyond the cosmic event horizon each year, crossing into regions we can never reach. The universe simultaneously reveals itself and escapes us. Think of it as two competing effects. Light from distant galaxies takes time to reach us. This delay means we're constantly seeing new galaxies for the first time as their ancient light completes the journey. Meanwhile, expansion pushes galaxies farther apart. The most distant ones recede faster than light. Eventually, they cross a threshold where future light they emit will never reach Earth. We can still see their past light arriving now, but they've moved into a causally disconnected region. This creates a strange asymmetry. Look at a galaxy 45 billion light-years away. You see light it emitted 13 billion years ago when it was much closer. That light took 13 billion years to reach you, but during that time, expansion carried the galaxy much farther away. Today, it sits 45 billion light-years distant. New light, leaving that galaxy now, will never reach Earth. Expansion carries it away faster than it can approach. Future civilizations in our galaxy will look up at a smaller sky. Galaxies visible to us will have vanished beyond their event horizon. Their observable universe will be more limited than ours. If civilizations arise, trillions of years in the future, after dark energy has pushed most galaxies beyond reach, they'll see only the galaxies bound to ours by gravity. A small local cluster, surrounded by emptiness. No cosmic microwave background. No evidence of the Big Bang. No expansion to measure. Those future astronomers might conclude they live in a static island universe surrounded by infinite empty space. They'd be wrong, but they'd have no way to know. The evidence would be gone. We live in a privileged time. The universe is still revealing its secrets, but the window is closing. Word count, 600 words. Chapter 19. Light that will never reach us. Right now, a galaxy 47 billion light-years away is emitting light. Photons stream from its stars in all directions. Some of those photons head toward Earth. They travel at light speed, the fastest anything can move through space. But they will never arrive. The space between that galaxy and Earth expands faster than light can cross it. Those photons are running on an expanding treadmill, making no progress toward their destination. This seems impossible. Light travels at 186,000 miles per second. How can space expand faster? The answer is that space itself has no speed limit. Einstein's cosmic speed limit applies to objects moving through space. It doesn't constrain the expansion of space itself. Add up all the expanding space across 47 billion light-years, and the total expansion rate exceeds light speed. The photon doesn't violate relativity. It travels at light speed through its local space, but local space continuously stretches. The photon covers distance at the maximum possible rate, yet the destination recedes faster than the photon can approach. Imagine running forward on a treadmill that moves backward faster than you run. You're running at your maximum speed. The treadmill simply moves faster. Your position relative to the room moves backward, despite your forward running. Light from beyond the cosmic event horizon experiences exactly this. The event horizon currently sits approximately 16 billion light-years from Earth. Galaxies beyond this distance recede faster than light. Photons they emit toward us make no net progress. They're trapped in expanding space, forever traveling toward Earth but never getting closer. Yet, we can see galaxies far beyond 16 billion light-years. How? Because we're looking at ancient light. A galaxy now 50 billion light-years away sent light toward Earth 13 billion years ago. Back then, that galaxy was much closer, perhaps only 3 billion light-years away. Space expanded slowly enough that the light made progress. Over billions of years, the photon crossed expanding space, eventually reaching Earth. But that same galaxy's current light will never reach us. We see its past. Its present is hidden behind an insurmountable barrier. The light leaving it now faces too much expanding space. It cannot overcome the expansion rate. Future civilizations in our galaxy will never see light emitted today from distant galaxies. That light is lost to expansion. This creates a peculiar situation. Galaxies are constantly disappearing from our causal future while appearing in our observable past. New galaxies become visible as their ancient light finally arrives. Simultaneously, those same galaxies cross beyond the event horizon in present time, cutting off future communication. We're watching a cosmic disappearing act. The universe reveals its past while hiding its present. Consider what this means. Somewhere in the universe, 45 billion light-years away, another civilization might exist. They're looking toward Earth with their telescopes. They see light our galaxy emitted 13 billion years ago. They see the Milky Way as it was in its youth. But they cannot see us now. Our current light will never reach them. Similarly, we cannot see them now. Their present light will never reach us. We are causally disconnected. We share the same universe but can never interact. No signal we send will cross the expanding space between us. No message they send will arrive here. We might as well exist in separate universes. And every day, more galaxies slip beyond this horizon. The universe is becoming lonelier. Word count. 600 words. Chapter 20. The speed barrier that isn't. Einstein proved nothing can exceed light speed through space. This is absolute. Accelerate a particle and its mass increases. Approach light speed and mass approaches infinity. You'd need infinite energy to reach light speed, let alone exceed it. The cosmic speed limit is unbreakable for anything moving through space. Yet distant galaxies recede at several times light speed. How do we reconcile this apparent contradiction? The answer distinguishes between two types of motion. Proper motion is movement through space. A spacecraft firing engines moves through space. A galaxy pulled by another galaxy's gravity moves through space. This motion obeys Einstein's speed limit. Nothing with mass can exceed light speed this way. Trying to do so requires more energy than exists in the universe. Recession velocity is different. This is the apparent motion caused by space itself expanding. A galaxy sitting in its local space might move at only a few hundred miles per second through that space. But the space between us and that galaxy stretches. All the expanding space across billions of light-years adds up. The galaxy appears to recede at tremendous speed, possibly exceeding light speed, even though it's barely moving through its local space. Think of ants on a rubber sheet again. Each ant walks at 1 inch per second through the rubber. This is proper motion through space. But stretch the rubber and ants at opposite ends separate faster than 1 inch per second. The extra separation comes from the rubber expanding, not from the ants walking faster. The ants never exceed their local speed limit. The sheet simply grows beneath them. Galaxies work identically. A galaxy 20 billion light-years away might move through its local space at a few hundred miles per second due to gravitational interactions with neighbors. This is well below light speed. But the space between us and it expands at a rate determined by the Hubble constant. Multiply 46 miles per second per megaparsec by the number of megaparsecs between us, and you get a recession velocity exceeding light speed. This doesn't transmit information faster than light. You cannot use expanding space to send a message that breaks causality. Light still travels at light speed through local space. A photon emitted by a distant galaxy travels toward Earth at light speed. But if the galaxy recedes faster than light due to expansion, the photon makes no net progress. It's like sending a message to someone running away from you faster than your messenger can run. The messenger obeys the speed limit. The target simply outruns them. General relativity explicitly allows this. Einstein's field equations describe space-time as dynamic. Space can curve, twist, expand, or contract at any rate. The constraint that nothing exceeds light speed applies only to motion through space-time, not to space-time itself changing. This is not a loophole, it's a fundamental feature of the theory. Some cosmologists have proposed using expansion to achieve faster-than-light travel. The Alcubierre drive, a theoretical propulsion system, would compress space in front of a spacecraft and expand it behind. The spacecraft wouldn't move through space. Space would move around it. You'd surf a wave of expanding space-time, potentially reaching distant stars in reasonable time without violating relativity. This remains pure speculation. Creating such a drive would require exotic matter with negative energy density. We don't know if such matter exists or can be manufactured. Even if possible, the energy requirements might exceed what any civilization could generate. For now, we remain limited, while the universe expands beyond our reach. Word count: 600 words. Chapter 21. Measuring distance in an expanding universe. Ask how far away a galaxy is, and you've asked an ambiguous question. Distance has multiple meanings in an expanding universe. The galaxy was a certain distance when it emitted the light we see. It traveled a different distance while that light journeyed to Earth. It sits at yet another distance right now. All three numbers differ, sometimes dramatically. Start with light travel distance. A galaxy's light took 10 billion years to reach Earth. You might say the galaxy is 10 billion light-years away, but this ignores expansion. During those 10 billion years, space stretched. The galaxy moved farther away while its light traveled. The light traveled more than 10 billion light-years through space to reach us. The actual path length might be 15 billion light-years due to the space that appeared during the journey. Next, consider proper distance. This measures how far away the galaxy sits right now, at this very moment, not where it was when it emitted light, where it is now. For the galaxy whose light took 10 billion years to reach us, proper distance might be 20 billion light-years. Expansion carried it much farther away during the light's journey. We see its past position. Its present position is much more distant. Then there's co-moving distance. This factors out expansion entirely. Imagine marking the galaxy's position on a grid that expands with space. As space stretches, the grid stretches, but the galaxy stays at the same grid coordinate. Co-moving distance measures separation on this expanding grid. It's constant over time, even as the physical distance increases. Cosmologists use co-moving distance because it simplifies calculations. You don't need to worry about how much space expanded at different times. Why does this matter? Because stating a distance without specifying which type leads to confusion. News articles report astronomers discovered a galaxy 13 billion light-years away. Which distance do they mean? Usually light travel distance. The light took 13 billion years to reach us, but the galaxy itself might now sit 30 billion light-years away. Its proper distance is more than twice its light travel distance. This complicates cosmic maps. Draw a map showing galaxy locations, and you must choose which distances to plot. Use proper distances, and you show where galaxies are now. but you're mapping positions you cannot directly observe. Use light travel distances, and you show a strange, warped map where closer objects appear from more recent times, and distant objects appear from the deep past. Use co-moving distances, and your map factors out expansion, showing the universe's structure without time evolution. Astronomers typically use co-moving distance because it makes mathematical models simpler, but this confuses the public. People naturally think in terms of proper distance. How far away is something right now? In daily life, this question has a clear answer. Your friend's house is 5 miles away right now. But for galaxies, right now is ambiguous because simultaneity breaks down over cosmic distances. General relativity says simultaneity is relative. Events that are simultaneous in one reference frame happen at different times in another frame. For nearby objects, moving slowly compared to light speed, this effect is negligible. But across billions of light years with expansion involved, simultaneity becomes deeply ambiguous. When you say a galaxy is 20 billion light years away right now, that right now is a choice of reference frame, not an absolute fact. The universe doesn't have a universal clock. Every observer carries their own time, and distances change between the ticks. Word count, 600 words. Chapter 22. The cosmic microwave background. 380,000 years after the Big Bang, the universe became transparent. Before this moment, space was too hot and dense for light to travel freely. Photons constantly scattered off free electrons, like trying to see through fog. Then the universe expanded and cooled enough for electrons to bond with protons, forming neutral hydrogen atoms. Suddenly, light could travel. The first photons to cross space freely flooded the universe in all directions. Those photons are still traveling. They've been journeying through space for 13.4 billion years. Expansion has stretched their wavelengths from visible light into microwaves. Today, they reach Earth from every direction as the cosmic microwave background. This is the oldest light we can detect, a baby picture of the universe, taken when it was a tiny fraction of its current age. Point a radio telescope at any patch of sky, and you'll detect this ancient light. It comes from everywhere: north, south, east, west, up, down, every direction. The entire sky glows faintly in microwaves with a temperature of 2.7 degrees above absolute zero. This is incredibly cold, but not absolute zero. The universe still carries heat from the Big Bang, stretched thin by expansion. What's remarkable is the uniformity. The temperature varies by only a few millionths of a degree across the entire sky. Look toward one galaxy cluster and measure 2.725 degrees. Look toward another and measure 2.726 degrees. The difference is microscopic. This tells us the early universe was extraordinarily smooth. No large variations in density, no massive structures yet, but the tiny variations matter enormously. They represent quantum fluctuations from the universe's first moments, stretched to cosmic size by inflation. Slightly denser regions appear slightly warmer in the microwave background. Slightly less dense regions appear cooler. These density differences seeded the formation of galaxies. Gravity amplified the denser regions over billions of years. They collapsed into galaxy clusters. The less dense regions became cosmic voids. The pattern of fluctuations matches predictions from inflation theory precisely. Measure the size and distribution of hot and cold spots in the microwave background, and you get specific numbers that inflation predicts. The match is so exact it's considered the strongest evidence that inflation actually occurred. Without inflation, there's no natural explanation for why the fluctuations have the exact pattern we observe. The microwave background also reveals the universe's composition. By analyzing its temperature variations, scientists calculate how much ordinary matter exists, how much dark matter, how much dark energy. The answers are startling. Ordinary matter, everything made of atoms, constitutes only 5% of the universe. Dark matter, invisible material detected only through gravity, makes up 27%. Dark energy, The mysterious force accelerating expansion comprises 68%. We are made of the rarest stuff in the universe. Everything you see, every star and planet and person, represents a tiny fraction of what exists. Most of the universe consists of things we cannot see and barely understand. The microwave background measurements confirmed this stunning fact. There's another implication. The microwave background represents a wall beyond which we cannot see. Before atoms formed, the universe was opaque. Light couldn't travel. We can calculate what happened earlier using physics, but we cannot observe it directly with light. The microwave background is the oldest image of the universe we'll ever capture with telescopes. To see further back requires different methods, gravitational waves perhaps, or neutrinos from the early universe. But the earliest moments remain hidden. Behind a veil of microwave light, word count, 600 words. Chapter 23. What we're expanding into is more universe. The question persists. If the universe is expanding, what is it expanding into? The answer challenges every intuition we have about space and existence. The universe is not expanding into anything. It's not growing into a pre-existing void. It's not filling empty space that was there before. The universe is expanding into more universe. Space itself grows. New distance comes into existence between existing points. Imagine you're trapped inside a three-dimensional video game. Your character can move north, south, east, west, up, down. These are the only directions. Now the programmers decide to expand the game world. They double all distances, mountains twice as far apart, cities separated by twice as much space. From your character's perspective, the world grew. But it didn't grow into anything external to the game. There is no external. The game world is the complete set of possible locations. Our universe works identically. Space is the set of all possible locations. You cannot exit this set because exiting would require going to a location, and all locations are already part of space. The concept of outside doesn't apply. Outside would be a place. All places are inside the universe by definition. When space expands, the set of locations grows in a specific mathematical sense. Distance between points increases. But this doesn't require the set to expand into something. The expansion is an intrinsic property of the geometry. Ask a mathematician about expanding manifolds, and they'll explain how a geometric object can grow without being embedded in a higher dimensional space. The growth is self-contained. This is profoundly difficult to visualize because we've never experienced anything like it. Every expansion we witness in daily life involves objects growing into surrounding space. Pour water and it spreads into the available volume. Inflate a balloon and it pushes into the surrounding air. These expansions require a container, a medium, an external space. Universal expansion requires none of these. The mistake is thinking of the universe as an object. Objects exist in space. They occupy volume. They have outsides and insides. The universe is not an object. It's the totality of physical existence. It's not in anything. It is everything. When cosmologists say space expands, they mean the fabric of physical existence increases in extent. This is a property of reality itself, not an object within reality. Some physicists have proposed our universe might be embedded in a higher dimensional space. String theory suggests 10 or 11 dimensions exist, most curled up microscopic small. Perhaps our three spatial dimensions expand through these higher dimensions. This is mathematically possible. It provides a container for expansion. But it's not necessary. General relativity describes expansion perfectly well without requiring extra dimensions. Furthermore, proposing higher dimensions doesn't truly solve the problem. It just pushes it back one level. If our universe expands into a higher dimensional space, what is that space expanding into? An even higher dimensional space? Where does it end? At some point, you need a space that simply exists without being contained in anything else. That's the universe. the fundamental layer of reality. Perhaps the question itself is flawed. Perhaps asking what the universe expands into assumes the wrong framework, like asking what time existed before time began. The question feels meaningful but points toward a confusion about the nature of space rather than a genuine mystery. The universe is not an object in space. The universe is space, and space is becoming larger. Word count: 600 words. Chapter 24. The multiverse possibility. What if our universe is just one bubble in an infinite cosmic foam? This is the multiverse hypothesis. It suggests the Big Bang that created our observable universe might not be unique. Perhaps countless other universes exist, each with its own space, time, and physical laws, each causally disconnected from the others, each an island of existence in a larger reality we cannot perceive. The idea emerges naturally from cosmic inflation. If inflation can start, it might never completely stop everywhere. Picture a boiling pot of water. Bubbles form, expand, and pop. Between the bubbles, more water keeps boiling, creating new bubbles. Eternal inflation works similarly. Most of space continues inflating forever, but occasionally, random quantum fluctuations cause inflation to stop in small regions. Each stopped region becomes a universe, a bubble of normal space surrounded by eternally inflating space. Our universe would be one such bubble. Inflation stopped here 13.8 billion years ago. Space expanded normally afterward. But beyond our cosmic horizon, in regions we cannot see, inflation might still continue, creating new bubbles, new universes, an endless process generating infinite variety. Each bubble universe might have different physical laws. The strength of gravity could vary. The mass of electrons might differ. The number of dimensions could change. In our universe, certain constants have very specific values that allow atoms to form and stars to burn. Change those values slightly and chemistry becomes impossible. Stars never ignite. Life never emerges. This leads to the anthropic principle. We observe a universe with life-friendly laws not because those laws are special, but because we can only exist in a universe where those laws hold. It's selection bias. Countless other universes might exist with different laws where observers never arise. We don't see those universes. We exist in one of the rare bubbles where conditions permit complexity. Critics argue the multiverse is untestable. If other universes are causally disconnected, we can never observe them. No experiment can confirm or refute their existence. This makes the multiverse more philosophy than physics. Science deals with testable predictions. The multiverse makes none. Supporters counter that inflation predicts eternal inflation as a natural consequence. If inflation happened once, it should happen indefinitely in most of space. The multiverse isn't an extra assumption. It's what inflation theory predicts when you follow the mathematics. Rejecting the multiverse means finding some mechanism that shuts down inflation everywhere simultaneously. That seems less natural than accepting that inflation continues. Some versions of quantum mechanics also suggest a multiverse, though different from the inflationary one. The many worlds interpretation says every quantum measurement creates a branching of reality. Each possible outcome occurs, but in separate branches. You observe one outcome in your branch. Other versions of you observe different outcomes in other branches. This creates a constantly branching tree of parallel realities, all equally real. Whether any of this is true remains unknown. We cannot detect other universes. We cannot visit them. We cannot communicate across the boundaries. If they exist, they're forever beyond our reach. More isolated than the most distant galaxy. Not separated by distance, separated by the fundamental structure of reality itself. Yet the question matters philosophically. If our universe is all that exists, its properties demand explanation. Why these laws? Why these constants? If countless universes exist with varying properties, ours needs no special explanation. We exist in one of the rare ones where existence like ours is possible, a lonely universe or infinite variety. Both possibilities are staggering. Word count: 600 words. Chapter 25. Higher dimensions we cannot see. We perceive 3 dimensions of space: forward, backward, left, right, up, down. These directions define every position, every motion, every structure in our experience. But physics suggests additional dimensions might exist, curled up so small we never notice them. Imagine an ant walking on a wire. The ant perceives 1 dimension of motion, forward and backward along the wire. But the wire itself has thickness. A tiny circular dimension wraps around the wire's circumference. The ant could walk around this circle, but the circle is so small the ant barely notices. To the ant, the wire seems one-dimensional. We might be similar, 3 large dimensions we navigate daily, but additional dimensions curled into circles so tiny they're invisible at human scales, perhaps trillions of times smaller than atoms. At those scales, particles could move through extra dimensions. This motion would appear as strange properties in our 3-dimensional perspective. Properties we interpret as charge or quantum spin might actually be motion through hidden dimensions. String theory requires these extra dimensions. The mathematics doesn't work in just 3 spatial dimensions. Particles aren't point-like in string theory. They're tiny vibrating strings. The way a string vibrates determines what particle it becomes. An electron is one vibration pattern, a quark is another. But these vibrations need extra dimensions to vibrate through. Specifically, string theory needs 10 or 11 total dimensions. 3 large ones we see, 6 or 7 tiny ones we don't. If extra dimensions exist, could the universe expand through them? Picture a balloon expanding. Its 2-dimensional surface grows through the 3rd dimension. Perhaps our 3-dimensional space expands through a 4th spatial dimension similarly. This would provide the outside that expanding into seems to require. Our universe would be a growing 3-dimensional surface embedded in a higher dimensional space. This idea appeals to intuition. It gives expansion a direction, a place to expand into, but it's not necessary. General relativity describes expansion without requiring extra dimensions. Space can grow intrinsically without being embedded in anything higher. The extra dimensions, if they exist, might be completely irrelevant to expansion. Moreover, proposing expansion through a 4th dimension doesn't truly solve the original puzzle. It replaces one question with another. What is the 4th dimension expanding into? A 5th dimension. And what's that expanding into? At some level, you need a space that simply grows without expanding into anything external. If the 4th dimension can do this, why can't our 3 dimensions? Still, extra dimensions offer interesting possibilities. Maybe the Big Bang happened in higher dimensional space. Maybe our 3 dimensions split off from a larger dimensional structure. Maybe time itself is actually a spatial dimension we experience sequentially due to our peculiar perspective. These ideas remain highly speculative, supported more by mathematical elegance than experimental evidence. We've tried detecting extra dimensions. Particle accelerators smash protons together at tremendous energies, searching for signs that energy disappears into hidden dimensions. So far, nothing. Gravitational wave detectors measure space-time ripples, looking for patterns that suggest gravity leaks into extra dimensions. So far, nothing. The extra dimensions, if they exist, remain stubbornly hidden. Perhaps they're too small. Perhaps we're not looking correctly. Perhaps they don't exist at all. And string theory needs revision. The mathematics is beautiful, but nature doesn't always care about mathematical beauty. Reality follows its own rules. Whether extra dimensions exist or not, they don't change the fundamental answer to the expansion question. Space grows, not through anything, just grows. Word count: 600 words. Chapter 26. The cosmological constant problem. Einstein added a term to his equations, a fudge factor. He called it the cosmological constant. Its purpose was to balance gravity and keep the universe static, which Einstein believed must be the case. Then Hubble proved the universe expands. Einstein removed the constant, reportedly calling it his greatest blunder. Decades later, astronomers discovered dark energy accelerating expansion. The cosmological constant came back. Einstein's blunder was correct after all. The cosmological constant represents the energy density of empty space. It's the same everywhere and never changes. Each cubic inch of vacuum contains a specific amount of energy. As space expands, new cubic inches appear, but each one has the same energy density as existing ones. The total energy increases. This energy creates negative pressure that pushes space apart. Here's the problem. Calculate what the cosmological constant should be based on quantum field theory, and you get an absurdly wrong answer. Quantum mechanics predicts virtual particles constantly pop in and out of existence throughout space. Each virtual particle contributes energy to the vacuum. Add up all possible virtual particles, and you get a vacuum energy density roughly 10 to the power of 120 times larger than observed. This is not a small discrepancy. This is the worst prediction in the history of physics. Theory and observation disagree by more than 100 orders of magnitude. If quantum field theory's prediction were correct, the universe would tear itself apart in a fraction of a second. Expansion would accelerate so violently that atoms couldn't form. Stars would be impossible. Galaxies would never exist. Yet here we are, in a universe where the cosmological constant is tiny but non-zero. Something must cancel most of the vacuum energy. Different contributions must subtract from each other with extraordinary precision, leaving only a tiny remainder. But why? Random cancellation seems impossibly unlikely. It's like randomly throwing darts at a board and having them all land within a millimeter of each other. Possible, but so improbable it demands explanation. Some physicists invoke the anthropic principle. Perhaps the cosmological constant varies across different regions of the multiverse. Most regions have huge values that prevent structure formation. We exist in a rare region where the constant happens to be small enough for galaxies to form and life to emerge. We observe a small cosmological constant because we can only exist where it's small. This explanation troubles many scientists. It abandons predictive power. If the cosmological constant can have any value, and we just happen to live where it's small, physics loses its ability to explain why things are the way they are. We're left with, it's this way because if it weren't, we wouldn't be here to ask. That's not satisfying. Others propose the cosmological constant might change over time. Maybe it was larger in the past. Maybe it will grow or shrink in the future. Current observations suggest it's constant, but we've only measured it over a tiny fraction of cosmic history. Long-term evolution could be too slow to detect yet. Some suggest we're misunderstanding quantum field theory. Maybe vacuum energy doesn't contribute to the cosmological constant the way we think. Maybe gravity responds differently to vacuum energy than to ordinary energy. Maybe general relativity needs modification at cosmic scales. None of these solutions satisfy everyone. The cosmological constant problem remains unsolved. A stark reminder that despite our progress, fundamental gaps persist in our understanding. The universe hides its deepest secrets behind simple-looking equations. Word count, 600 words. Chapter 27. Acceleration was a complete surprise. In 1998, two teams of astronomers independently dropped a bombshell on physics. They'd been studying distant supernovae, expecting to measure how much gravity was slowing the universe's expansion. Instead, they found expansion speeding up, not slowing, accelerating, growing faster over time rather than decelerating as everyone predicted. This was so unexpected that both teams spent years checking for errors before publishing. They examined their telescopes, recalibrated their instruments, questioned their assumptions, looked for any possible mistake. The data kept showing the same result. Distant supernovae appeared dimmer than they should if expansion were slowing. The only explanation was that space had expanded more than expected. Expansion was accelerating. The physics community reacted with skepticism, bordering on disbelief. Accelerating expansion violated everything cosmologists thought they knew. Gravity pulls matter together. The universe contains enormous amounts of matter. All that matter should slow expansion over time, like a ball thrown upwards slowing as gravity pulls it back. Instead, expansion was speeding up, as if someone kept throwing the ball faster the higher it went. What could cause this? The only known force strong enough was Einstein's cosmological constant, the energy of empty space itself, pushing space apart with negative pressure. But Einstein had removed this from his equations decades earlier. Reintroducing it felt like admitting defeat, like adding a fudge factor to fix broken predictions. Yet the evidence became overwhelming. More supernovae confirmed the effect. Measurements of the cosmic microwave background agreed. Surveys of galaxy distributions matched predictions for an accelerating universe. By 2003, the scientific consensus accepted acceleration as real. The Discovery team won the Nobel Prize in 2011. Dark energy became the term for whatever was causing acceleration. Not because we know what it is. The name simply labels our ignorance. It's dark because we cannot see it. It's energy because it affects the universe's expansion. That's all we know. We don't know what it's made of. We don't know why it exists. We don't know if it's truly constant or slowly changing. Multiple theories compete to explain dark energy. Maybe it's the cosmological constant, vacuum energy that never changes. Maybe it's a dynamic field called quintessence that evolves over time. Maybe gravity itself behaves differently at cosmic scales, and we're misinterpreting the equations. Maybe extra dimensions leak gravitational effects into our space, creating an illusion of dark energy. Testing these theories requires precise measurements of expansion over cosmic time. Observe supernovae at different distances, and you map expansion history. Study how galaxies cluster, and you probe dark energy's effect on structure formation. Measure gravitational lensing, and you test whether gravity behaves as general relativity predicts on large scales. So far, all observations match the simplest model. Dark energy behaves like Einstein's cosmological constant, fixed density, never changing. This is both reassuring and frustrating. Reassuring because general relativity keeps working. Frustrating because we still don't understand why the cosmological constant has the value it does. The discovery of accelerating expansion changed cosmology forever. Before 1998, cosmologists debated whether the universe would expand forever or eventually collapse. Acceleration settled that debate. The universe will expand forever, growing ever larger and emptier. But it raised deeper questions we still cannot answer, about the nature of space and the fate that awaits us. Word count, 600 words. Chapter 28. The Big Rip Scenario. Imagine the universe accelerating so violently that it tears itself apart, not in the distant future. In a finite time that's calculable, galaxies shredded, stars ripped from their orbits, planets pulled into fragments, atoms themselves disintegrated by expansion, growing so fast that nuclear forces can no longer hold them together. This is the Big Rip, the most extreme possible fate for an accelerating universe. The scenario requires dark energy to strengthen over time. If dark energy maintains constant density as space expands, acceleration continues forever but approaches a steady rate. Distant galaxies vanish beyond our horizon. The universe grows cold and dark, but stable structures like galaxies and solar systems survive indefinitely. Gravity holds them together against the gentle tug of expansion. But if dark energy grows stronger, everything changes. Phantom energy is the term physicists use for dark energy that increases in density as the universe ages. This creates runaway acceleration. More expansion creates more dark energy. More dark energy drives faster expansion. The feedback loop amplifies until expansion rates become catastrophic. Here's how it would unfold. Currently, dark energy only affects the largest scales. Galaxy clusters slowly drift apart. Individual galaxies remain stable. Solar systems are completely unaffected. Expansion is too weak to overcome local gravity. But as phantom energy strengthens, expansion accelerates. The rate at which space grows increases exponentially. 20 billion years from now, galaxy clusters tear apart. The Milky Way loses its neighboring galaxies. They recede beyond reach, their light fading into darkness. 60 million years before the end, galaxies themselves disintegrate. Stars rip away from each other. The Milky Way's spiral structure shreds. Individual stars float alone in expanding space. 3 months before the end, solar systems break. Earth leaves its orbit around the Sunday. The sun drifts away. Planets scatter into darkness. Each world becomes an island in space that grows faster than light can cross it. 30 minutes before the end, planets themselves fragment. Earth's surface tears apart. Mountains float away. Oceans evaporate into space. The planet dissolves. In the final fraction of a second, atoms disintegrate. Molecules break apart. Nuclear forces cannot overcome expansion, pulling protons and neutrons away from each other. Atomic nuclei split. Then fundamental particles themselves might shred, ripped into their constituent quarks by space expanding faster than the strong force propagates. Everything ends. Every structure destroyed by expansion grown so powerful that nothing can resist it. The universe doesn't fade into cold darkness. It violently tears itself apart in a cataclysm that destroys everything that exists. This sounds like science fiction, but it's mathematically possible if dark energy has the right properties. The question is whether dark energy actually behaves this way. Current measurements suggest it doesn't. Dark energy appears constant or very slowly changing. The Big Rip remains a theoretical possibility, but not a prediction. Still, we cannot rule it out. Our measurements cover only the last few billion years of cosmic history. Dark energy might evolve slowly enough that we haven't detected the change yet. If it strengthens gradually, the Big Rip could be trillions of years away, far enough that we cannot see it coming. Or dark energy might stay constant. Expansion continues forever, but gently. Galaxies drift apart. Stars die. The universe grows cold, but nothing tears apart. Heat death, rather than violent destruction. Either way, the expansion we see today determines our ultimate fate, a future written in the fabric of space. Trillions of years from now, the last stars will die. Galaxies will have long since drifted beyond sight of each other, isolated islands in an ocean of expanding space. No new stars will form. The gas that makes stars will have been used up or dispersed too thin to collapse. Red dwarfs, the smallest and longest-lived stars, will slowly cool over incomprehensible ages. Eventually, even they'll exhaust their fuel. The universe will contain only dead stars. White dwarfs cooling slowly toward absolute zero. Neutron stars spinning alone in darkness. Black holes evaporating gradually through Hawking radiation. Expansion continues throughout all this, pulling the remnants farther apart. The space between objects grows until each galaxy cluster becomes an isolated system, causally disconnected from all others. Within these isolated islands, matter slowly decays. Protons might be stable forever, or they might decay over timescales of 10 to the 34 years. If they decay, all atoms eventually disintegrate. Planets crumble into radiation. Moons vanish. Rocky debris dissolves into photons and neutrinos. Even black holes aren't permanent. They emit Hawking radiation, slowly losing mass. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely. By 10 to the 100 years, even the largest black holes have evaporated. The universe contains only photons, neutrinos, and perhaps some exotic particles. These particles spread thinner as expansion continues. Eventually, the distance between any two particles exceeds what light could cross, even if given infinite time. Each particle exists in complete isolation, unable to interact with anything else ever again. This is heat death, maximum entropy, perfect equilibrium, no gradients, no energy flows, no structure, no change. The universe has expanded and cooled until nothing can happen anymore. Time becomes meaningless because nothing marks its passage. Events require change. Heat death is changeless. But expansion continues. Space keeps growing even in this dead universe. The distance between particles increases exponentially. The temperature approaches absolute zero asymptotically. Dark energy, unchanged by the death of matter and stars, pushes space apart at the same steady rate it always has. Some physicists speculate about what might come after heat death. Quantum fluctuations occur even in empty space. Given infinite time, a fluctuation could spontaneously create a new universe. The probability is infinitesimally small, but infinity is long. Eventually, even impossibly rare events occur. New Big Bangs might emerge from quantum fluctuations in the far future of our universe's heat death. These new universes would be causally disconnected from the previous one. They'd have their own space, time, and physical laws. The old universe continues existing, dead and dark and ever expanding. The new universe begins fresh. Infinite time produces infinite possibilities. Others suggest consciousness might find a way to survive. Advanced civilizations might upload themselves into substrates that require minimal energy, slow their thinking to match the dwindling energy available. As the universe cools, they cool too, thinking ever slower but potentially continuing indefinitely. A single thought taking billions of years but containing subjective eternity. These ideas are speculative. We don't know if consciousness can persist in such extreme conditions. We don't know if the laws of thermodynamics allow infinite information processing with finite energy. We're extrapolating physics far beyond what we can test. What's certain is this: expansion continues regardless. Long after the last star dies, long after the last black hole evaporates, long after every structure dissolves, space keeps growing, empty and dark, forever. There's a limit to what physics can answer. Not because our technology is insufficient, not because our theories are incomplete, because the universe itself places boundaries on knowledge. Some questions cannot be answered even in principle, blocked by fundamental barriers built into the structure of reality. Consider the question of what lies beyond our cosmic horizon. Light from those regions has not reached Earth and never will. Expansion carries them away faster than their light can approach. We cannot observe them. We cannot measure them. We cannot send signals to them or receive signals from them. Any statement about those regions is untestable. Science requires testability. A hypothesis must make predictions that observations can confirm or refute. If a claim predicts nothing observable, it's not scientific. It's philosophy or speculation. This doesn't mean such claims are false. They're simply beyond the domain where science operates. The regions beyond our cosmic horizon might be filled with galaxies, or they might be empty, or they might follow different physical laws. We cannot know. The same limitation applies to the universe before the Big Bang. If time itself began at the Big Bang, asking what came before is asking about something outside time. This might be meaningless, like asking what's north of the North Pole, or it might point to a different kind of causation we don't understand. Either way, we cannot observe anything before the Big Bang. The cosmic microwave background represents an impenetrable barrier. We can speculate, but we cannot test. Quantum mechanics adds another layer of unknowability. The uncertainty principle isn't about measurement limitations. It states that certain pairs of properties fundamentally lack simultaneous, precise values. A particle doesn't have an exact position and exact momentum. It exists in a state where both are indeterminate. Measuring one property collapses the state, making the other property even less determinate. This isn't ignorance. It's fundamental indeterminacy built into reality. Then there's Gödel's incompleteness theorems. These mathematical results prove that any sufficiently complex logical system contains statements that are true but cannot be proven within that system. Applied to physics, this suggests our mathematical descriptions of the universe might always be incomplete. Some true statements about physical law might be forever unprovable. Does this mean we should abandon science? No. It means we should recognize its boundaries. Science is extraordinarily powerful within its domain. It predicts, explains, and controls natural phenomena with stunning accuracy. But it cannot answer every question. Some questions lie beyond the reach of observation and experiment. What is the universe expanding into? Science answers. The question assumes the wrong framework. Space doesn't need to expand into anything, but this feels unsatisfying. The human mind craves an external container. Science cannot provide one because none exists. This is a limit of our intuition, not a failure of physics. Why does the universe exist instead of nothing? Science has no answer. It can trace causation back to the Big Bang. It can speculate about quantum fluctuations creating universes. But why do quantum laws exist? Why does anything exist? These questions might be unanswerable. Some philosophers suggest we're asking the wrong questions. Maybe existence doesn't require explanation. Maybe the universe is brute fact. Maybe our demand for ultimate answers reflects human psychology rather than a genuine feature of reality. We live in a universe that reveals itself slowly, but also keeps eternal secrets, and we must learn to live with both. Cosmologists describe the universe using mathematics. Equations govern expansion. Geometry describes space-time curvature. Numbers predict how galaxies move. But here's a strange question. Is the universe actually made of mathematics, or does mathematics merely describe the universe? Does space exist independently of our equations, or is it nothing more than the mathematical relationships themselves? Some physicists argue the universe is fundamentally mathematical. Max Tegmark proposed the mathematical universe hypothesis, stating that physical reality is a mathematical structure, not described by mathematics, not represented by mathematics, actually is mathematics. The universe doesn't contain mathematical relationships. It is those relationships. Physical objects are mathematical objects. Space is a geometric structure. Time is a parameter in equations. Everything reduces to pure mathematics. This idea has appeal. Mathematics is timeless and spaceless. It doesn't require creation or explanation. The Pythagorean theorem is true whether humans exist or not, whether the universe exists or not. It's simply true as a matter of logical necessity. If the universe is mathematical, it doesn't need a creator or a cause. It exists because mathematical structures exist, and mathematical existence is necessary. But this leads to puzzling questions. If all mathematical structures exist as universes, why do we experience this particular one? Why these equations and not others? Tegmark suggests all consistent mathematical structures exist as separate universes. We inhabit one particular structure because it's complex enough to support conscious observers. Again, the anthropic principle. We observe this universe because we can only exist in this universe. Other physicists reject this. They argue mathematics is a human invention, a language we created to describe patterns in nature. The universe contains real physical stuff that behaves in certain ways. We notice patterns and develop mathematical models. The models are useful descriptions, but not the underlying reality. Space is something that genuinely exists, not merely a geometric abstraction. This view treats mathematics as a map and the universe as territory. Maps are useful. They guide navigation. But the map isn't the terrain. You cannot walk on a paper map. Similarly, equations predict how objects move through space. But the equations aren't space itself. Space is whatever's really there when you remove the mathematical description. But what is there when you remove mathematics? What is space made of? General relativity describes it as a geometric structure with curvature. Remove that description, and what remains? An empty concept? Maybe we cannot understand space except through mathematics. Maybe mathematics isn't just a description, but the only way space can be understood. Consider a simpler example. What is a circle? You can define it mathematically as the set of points equidistant from a center. That's abstract. Or you can draw a circle on paper. That's physical. But the drawn circle isn't perfectly circular. It has bumps and variations. Only the mathematical circle is perfect. So which is more real? The imperfect physical circle or the perfect mathematical form? Plato argued the mathematical form is more real. Physical circles are imperfect shadows of the perfect ideal circle. The mathematical realm is the ultimate reality. Physical reality is derivative. Modern Platonists like Tegmark echo this view. Mathematics is primary. Physics is applied mathematics. Others reverse the priority. Physical reality is primary. Mathematics is a human tool for understanding it. The universe would exist even if mathematics was never invented. Perhaps the debate is unsolvable. Perhaps asking whether space is mathematical or physical is like asking whether light is waves or particles. It's both, or neither, or the question itself is wrong. You'll never travel to another galaxy. Neither will your children, grandchildren, or distant descendants 1,000 generations from now. Expansion ensures this. The nearest major galaxy sits 2.5 million light-years away. Even traveling at light speed, the journey would take longer than human civilization has existed. And light speed is impossible for massive objects. Realistically, intergalactic travel is forever beyond reach. This should trouble us. It means the universe is mostly inaccessible. We're trapped in our local galaxy cluster, which gravity holds together against expansion. A few dozen galaxies, a tiny island in an ocean of space we can never cross. Everything beyond this island will eventually disappear beyond our cosmic horizon as expansion accelerates. Future generations will look up at a smaller sky. Yet understanding this limitation matters profoundly. It shapes how we think about humanity's place in existence. Are we significant? We occupy a planet orbiting an ordinary star in an unremarkable galaxy, which itself is one of trillions we'll never reach. Expansion ensures our permanent isolation. If significance requires cosmic importance, we have none. But perhaps significance doesn't require cosmic importance. Perhaps meaning is local. You matter to people around you. Your actions affect your community. Your ideas influence culture. These effects ripple outward, limited by light speed and expansion, but genuine within their scope. The universe's vast indifference doesn't negate local meaning. Understanding expansion also clarifies our origins. We exist because the universe expanded and cooled at a specific rate. Too fast and matter would never clump into galaxies. Too slow and everything would collapse into black holes before stars could form. The expansion rate had to fall within a narrow range for structures like galaxies to exist. This is another anthropic observation. We observe this expansion rate because we can only exist if the rate is this value. Some find this depressing. Our existence is an accident of cosmic parameters. Change one number slightly and we never arise. Others find it liberating. The universe doesn't care about us, which means we're free to create our own meaning and purpose. No cosmic plan constrains us. No universal significance burdens us. We're gloriously insignificant, free to define ourselves. The question of what the universe expands into also touches our psychology. Humans need containers. We think in terms of boundaries and exteriors. The universe has neither. This conflicts with our cognitive architecture. We evolved to navigate three-dimensional environments with edges and surfaces. The universe defies this intuition. There's no outside, no boundary, no container. Accepting this requires cognitive humility. Our intuitions evolved to solve local problems, not cosmic ones. Expecting the universe to conform to human intuition is backwards. The universe operates according to its laws. We must adapt our thinking to match reality, not demand that reality match our expectations. This is uncomfortable. It means much of the universe is fundamentally strange. We can describe it mathematically, we can make predictions, but we cannot visualize it or understand it in the same way we understand everyday objects. The universe operates at scales where human intuition fails. Living with this discomfort is part of being human in a scientific age. We've discovered we live in a universe far stranger than our ancestors imagined, vast beyond comprehension, mostly empty, expanding forever, fundamentally unknowable in key respects, yet also beautiful, governed by laws we can discover and worth understanding. Here's a paradox. The universe is infinite. It contains infinite space, infinite matter, infinite galaxies, yet it's also expanding, growing larger. But how can infinity grow? Isn't infinity already the largest possible size? Add anything to infinity and you still have infinity. So what does it mean for an infinite universe to expand? The resolution requires careful thinking about infinity. Not all infinities are equal. Mathematicians distinguish between different sizes of infinity. Some infinities are genuinely larger than others. But that's not what's happening with universal expansion. The universe isn't becoming a larger infinity. It's expanding in a different sense. Think of infinite space as a grid, extending forever in all directions. Each grid square measures 1 inch on a side. The grid is infinite. Now expand the grid. Each square becomes 2 inches on a side. The grid is still infinite. Same number of squares extending forever. But the metric, the measurement of distance, has doubled. The grid is larger in the sense that distance between any 2 points has increased. This is metric expansion applied to infinite space. Space remains infinite but becomes more spread out. Galaxies sit at specific grid coordinates. As the grid expands, the physical distance between galaxies increases. The number of galaxies doesn't change. Their grid positions don't change. The distance between them changes. So an infinite universe can expand without becoming a larger infinity. It expands by increasing distances. This sounds paradoxical because we're used to expansion meaning containing more stuff. But universal expansion means having larger distances rather than containing more space. Space was already infinite. Distances within that space grow. Another way to think about it, expansion doesn't add new space at the edges because there are no edges. Expansion adds new space between existing points. Every distance increases proportionally. A region 1 million light-years across becomes 2 million light-years across. A region 1 billion light-years across becomes 2 billion light-years across. Both doubled in size, but both were already parts of an infinite whole. This works even if the universe is finite. A finite universe with no boundary, curved back on itself like a sphere's surface, can also expand. The total volume increases, but there's still no edge. The surface area of a sphere can double without requiring the sphere to be embedded in a larger space. It just grows. A three-dimensional finite universe does the same. The paradox arises from conflating two concepts: size in the sense of how much there is, and size in the sense of how far apart things are. An infinite universe is maximally large in the first sense. You cannot have more than infinite space, but it can grow in the second sense. Distances between objects can increase without limit. This creates strange situations. The observable universe is finite and growing. We see more galaxies each year as light from farther distances reaches us. But the total universe might be infinite and also growing. The observable finite part grows. The infinite whole grows. Both statements are simultaneously true without contradiction. Mathematics handles this easily. Infinity plus infinity equals infinity. 2 times infinity equals infinity. The equations work perfectly. Only our intuition struggles. We want infinity to be a fixed maximum. But infinity isn't a number. It's a concept describing something without bound. Something without bound can still expand. The universe doesn't care about our confusion. It simply grows, forever. We've traveled through cosmic history, from the first moment of expansion to the final heat death trillions of years hence. We've explored quantum fluctuations, dark energy, event horizons, and the shape of space itself. We've confronted the strangeness of a universe that expands without expanding into anything. Yet one truth persists through all this. The deepest questions remain unanswered. Science has revealed an astonishing cosmos. The universe is 13.8 billion years old. It contains 2 trillion galaxies, each with hundreds of billions of stars. Space itself is fabric that can stretch, curve, and grow. Dark energy accelerates expansion. Dark matter holds galaxies together. The cosmic microwave background preserves an image of the universe when it was 380,000 years old. These discoveries are remarkable. A century ago, we thought the Milky Way was the entire universe. We didn't know about other galaxies. We didn't know space expands. We didn't know about the Big Bang or dark energy. Our understanding has exploded in the brief span of a few human lifetimes. Yet fundamental mysteries persist. What is dark energy? Why does it have the value it does? What is dark matter? Is it particles we haven't detected yet, or something stranger? Did anything exist before the Big Bang? If so, what? Is our universe alone, or do countless others exist? Is the universe finite or infinite? Will expansion continue forever, or could it reverse? Most profoundly, what is space itself? General relativity describes it as a geometric structure. Quantum mechanics suggests it's made of fields and foam at the smallest scales. String theory proposes it has hidden dimensions, but these are mathematical descriptions. What is space really? What is it made of? Does that question even make sense? We've learned that space can expand without expanding into anything. This answer feels incomplete. It tells us what expansion isn't, but not what it fundamentally is. We've translated the mystery into mathematics. We can predict expansion rates, calculate distances, and model the universe's future. But prediction isn't understanding. We've quantified the phenomenon without truly grasping its nature. Perhaps this is the limit of human knowledge. Perhaps some aspects of reality transcend our capacity for intuitive understanding. Our brains evolved to hunt prey and gather food on African savannas. They didn't evolve to comprehend cosmic expansion or quantum mechanics. That we can understand anything about these topics is already remarkable. Or perhaps future generations will achieve breakthroughs we cannot imagine. New physics, new mathematics, new ways of thinking about space and time. Concepts that make current mysteries obvious. Just as relativity made Newtonian confusion about absolute time and space clear, perhaps some future theory will make expansion intuitively obvious. Until then, we live with uncertainty. We stand on a planet orbiting a star in a galaxy among trillions, watching the universe expand around us. We've measured that expansion, mapped its history, predicted its future. But the deepest question, the one that started this journey, remains incompletely answered. If nothing exists outside the universe, what is it expanding into? Science says nothing. The question assumes the wrong framework. Space doesn't expand into anything. It simply grows. This is the best answer we have. A correct answer. A true answer. But not a fully satisfying one. The universe keeps its ultimate secrets. And we continue reaching toward them, forever asking, forever wondering.